All right. Thank you so much, everyone, for joining. My name is Maya Wood. I am Technical Sales Officer with Normec OWS. I have been working at Normec OWS in this role for about 2 years now. And for my entire 20-year plus career, I have worked in the testing, inspection, and certification industry, much of that time focused on sustainability topics. I have also enjoyed sharing knowledge about our environment and sustainable practices with various schools in the area and have worked as an instructor to teach general biology lessons. So I'm very excited to be here to share some information with you all today with my colleague Ashley Tilot.
Hi, I'm Ashley. I have been at Normec OWS for almost 6 months, so still a newbie in the space specifically, but I was previously a customer of Normec OWS, and so I'm very familiar with the certification process and all that goes into it. I've been in the sustainability space for the last 3 years, and really just excited to share more about this space.
All right, Ashley. So I understand you've recently returned from some conferences, and I know that there are a lot of conversations going on about material circularity. And so I thought it'd just be nice to get together and share with everyone some of the questions that have been circulating about compostable products in particular.
Yeah, absolutely. So my first question is, when we think of compostable materials like packaging and food serviceware, I know contamination is something a lot of people are really concerned about. How can we be sure that a material will completely disappear when it's composted?
Sure. I mean, I know when I think about, or even before I joined Normec OWS, when I think about if something is compostable or not, this idea of it disappearing is kind of the first thing that comes to mind. And I think it's important to remember that a lot of compostable packaging material and food service items are made out of natural materials. They are designed to be able to disappear, if you will, in just the same way that other natural materials, apples, banana peels, and so on. Paper products are just designed to disappear. So this word disappearance, there's really one specific measurement that we do in the lab that relates to this idea that we're checking to make sure it's going to disappear. And that test is known as disintegration. So that makes sense. Disappears, disintegrates. And I know I like to think of things in terms of what is the measurement that we're taking when we do a particular test. Because when we're testing for compostability, that's really an overarching idea, and there are a lot of things that we need to check, disappearance or disintegration only being one of them. So the measurement that we're taking here is that we have this test material. Let's just say, for argument's sake, it's a packaging material and we are composting it. And over time, we're going to shake it through a sieve, and it's a sieve with 2 millimeter holes in it to ensure that it's going through the sieve, that it's breaking up into little tiny pieces. So we're looking at the physical breakdown, and then it's going to pass through that sieve. And at the end of this 12-week test, we need to make sure that at least 90% of that material is in fact breaking down and going through that sieve. This is really important to, professional composters because they have a product that they're selling, which is compost, and they want to make sure that they're not seeing any fork tines or little pieces of paper plate in their compost. They want it to look clean and completely degraded. A lot of times when this, contamination is seen, it's actually, non-certified materials that we're finding. So it's really just an issue of properly sorting. And then, the compostable material should break down just the same as the food waste and disappear completely so that we don't have these contamination concerns.
Okay. So after testing the disappearance or disintegration, how can we be certain that there's not just 100% of these like 1 millimeter microplastics left in our compost?
Yeah, I mean that's why we have to take this further when we look at when we look at our specifications like ASTM D6400 and BPI certification, we can't just rely on this disappearance to know that it is truly, completely, fully broken down. Because just as you said, I mean, that's a very extreme situation, but what if it was just 1 millimeter microplastics that are left behind? And so what we need to do then is biodegradation testing. And so now this is an entirely new test where we are looking at the chemical breakdown of the material, not just the physical breakdown of the material. And so again, I like to think of things in terms of the measurement that we're taking. And in this case, we are measuring carbon dioxide that is coming off from the test sample. So what is eating up these packaging materials and apples and the food scraps? Well, what's eating them up is the microbes, so our bacteria, our fungi. This is their food, and we want to ensure that they're converting it all the way to carbon dioxide, because in an aerobic environment, just like we operate as humans in an aerobic environment, we breathe out CO2. The microbes are respiring CO2. And so that is the measurement that we're taking. And we need to ensure that the chemical conversion to CO2 is taking place at least to 90%. So we're looking for a 90% evolution of carbon dioxide coming off from the test sample to know that we don't just have a bunch of little pieces of plastic. It's going all the way back to carbon dioxide, full biodegradation.
Great. So why isn't the pass rate 100%? Rather, it's 90%. We kind of come back to that 90%. Is the remaining 10% just like undegraded? Is it microplastic? Like, why is it that 90%?
Yeah, that's a great question. I think, we always want to be careful about claiming anything to be 100%. When you say 100%, that is, a numerical value. And we know that in the world of science, any test method that we would perform, doesn't matter what the test method is always going to have some level of uncertainty. So this usually kind of flags any kind of 100% claims as being a little bit concerning. So we know that we'll have some method uncertainty. Then we want to go back and think about, what is happening when the microbes are eating this packaging material as food and converting it to CO2. What's going on there? Well, they are respiring CO2. And then some of the material, some of the carbon, they're going to incorporate into their bodies. I mean, they don't have bodies, but into their cells, right? And be making the building blocks of life with some of that carbon. Just like when we eat our food, we're converting some of the carbon into the building blocks of life. We're then respiring CO2. So when they incorporate a little bit of that carbon, we call that biomass. So a little bit is going there. But even if we want to play devil's advocate and we're thinking about that 10% and we're really honing in on it, all right, well, we got to 90%, so the major ingredients of this packaging material we know had to be biodegradable, right? The major ingredient, to be able to get all the way up to 90%, we know the major ingredients had to be biodegradable. But what about some of these minor ingredients? So what the certifications do, like the BPI certification, is we kind of zoom in on those minor ingredients or ingredients present between 1 and 10% in a finished product. And coming up soon here in June, we're going to be bumping that up to any ingredient present in the formulation between 1 and 15%. And we're just going to zoom in on those ingredients. We're going to pull that ingredient out separately, like wherever we buy it from our supplier or whether we manufacture it ourselves. And we're going to do a biodegradation test and look chemically at what is happening on that one ingredient all by itself. And then that ingredient also needs to be converted all the way to 90% carbon dioxide. So if we do that with each of these minor ingredients within that percentage range, then we can be a lot more confident that, we don't have this situation with little minor ingredients are not breaking down or contributing to microplastics because we have checked all of the minor ingredients to ensure that they too are also being completely chemically broken down or biodegraded.
Great. Yeah, that sounds like we've covered that. I understand that biodegradation is being carefully evaluated, as you just kind of said, Maya. But what if there really is like a minor ingredient that's really toxic?
Okay, yeah, so this is really important. I know I worked as a toxicologist for a number of years, and evaluating toxicity is a really critical part of ensuring that we are moving collectively towards greener chemistries and greener formulations and greener materials in our future. So we don't want to leave this out. And ASTM D6400 definitely addresses the toxicity concerns, as do, the variety of certifications. We have to look at toxicity. We can't just say it's breaking down. We have to make sure this is not going to be toxic to the environment. So there are two ways in which we look at this. One of them is to kind of look for those big red flags, those toxic heavy metals, arsenic, lead, cadmium. We also want to look for PFAS. That's a big hot button issue and a major concern that we're not contributing these forever chemicals to our compost and to wherever the compost is used. So we will analytically test for those big red flag concerns. However, there are a lot of potential toxic chemicals out there in the world of commerce and material development. There's a lot of potential ones, whether it's pesticide residues, herbicides, what have you. So it would be really cost prohibitive to analytically test for every single potential chemical of concern. So we have kind of this insurance policy in the ecotoxicity testing that we do. And what we'll do is we will take two different species of plants, and we will repeat the test with these two different species of plants. We have our control group, which has compost that does not have the test item. So again, let's use a packaging material, or let's say it's a paper plate this time. So we've created compost just with food scraps, none of the paper plate test material. And then we have our test group where we've created compost, but we've loaded that compost up with many, many kilograms of this paper plate. And we are then going to grow our plants in the control group and the test group. And what we're looking for as evidence of toxicity is if the seeds are not germinating properly. So if we see the seeds in the test group are not germinating as well as the control group, then we have a concern here, and this item would not pass and would not be certified. So the seeds need to germinate just as well in test and control. And then the second area that we're looking at is, okay, the seeds germinated, the plant is growing, but we want to ensure that where the test material lies, that there's no stunted growth. So we measure the biomass of these plants to ensure that the plants are growing just as big and healthy in the test group as they are in the control group. And this is kind of our insurance policy, our catch-all for any other potential toxic effects. We can see that the plants are growing just as healthy in one group as the other.
Great. As you've been kind of talking through all of these different lab tests, they sound pretty comprehensive, but what about critics that are concerned about the fact that materials may behave differently in a lab compared to out in like the natural environment?
Sure. Yeah. I mean, we know we can never get rid of laboratory testing because we need to ensure that we're always comparing apples to apples. So if we want to be able to say, yes, this material can be certified and it was judged by the same set of rules as this other material over here, then we need to be able to use laboratory testing. We need to ensure that, material A from company A was tested at the same temperature and the same humidity under the same conditions as company B and their material B. So we always want to make sure we're comparing apples to apples. With that said, the development of the laboratory testing has been done in such a way that we're really trying to mimic as best we can the conditions that would be present in the real world environment. So for industrial compost certification, the temperature is mimicking what would be the case in an industrial facility, in an industrial technology, and in home composting certification, we're going to be seeing lower temperatures as we would in kind of a backyard environment. So we're trying to mimic the environment as best we can while still honoring the fact that in good science, we control all variables with the only changing variable being our test variable, which in this case is the presence of our test material or our paper plate. So with that said, that doesn't mean that we don't love field testing. Field testing is a wonderful complement to laboratory testing to be able to test something outdoors. Field testing is an example of a disintegration analysis done outside. It does not allow us, so it has the limitations of we can't measure CO2 evolution out in the field, so we can't really check on that chemical breakdown because we can't have, our gas chromatographs out there in the weather. But it is nice to, if you want to see how things are disintegrating out in the field in Texas in the summer and compare that to Ohio in the spring. It's nice insurance, from a marketing perspective to be able to do some field tests to ensure that these items also disintegrate in real world conditions and to play with the humidity, play with the temperature and see how things go. So it's not that one is better than the other, but it's a nice complement to be able to have field testing as well to see how things will be in the outdoors or in an actual industrial composting facility.
Perfect. So with all that you said, thank you very much, by the way. What final thoughts would you like to leave us with when it comes to compostable materials?
Yeah, I think it's important to remember that we're kind of all in this together and we need to embrace all solutions. Folks like myself who are enthusiastic about compostable materials, we absolutely recognize that they cannot replace all of the recycled materials out there and all of the fossil fuel based materials that are out there. However, and we completely respect the waste pyramid. If you've ever seen the waste pyramid, up at the top is the ideal scenario where we reuse our materials. We don't recycle them, we don't compost them, we reuse them. So, I was just playing with getting my RV ready for camping season this past weekend, and I brought in my propane tank to get refilled, and they said, oh, your propane tank's going to expire in August, just so you know, but I'm going to be able to take that over to Corrigan, and Corrigan is going to be able to recertify my propane tank and give it a new date stamp so I can reuse it again and again. Perfect ideal scenario. I'm not buying a new one and someone's not having to make a new one. I can just invest all of the energy that was made and keep using this one. Second, underneath that somewhere is recycling, and recycling is wonderful. It recaptures a good amount of the energy that was used to make the material. We still have the energy of the recycling process, and we may lose a little bit of material or function, but it's a great way, to maintain circularity. With that said, there are some items that don't. Well, we know that we can only recycle something a certain number of times, and there are also some items that don't lend themselves well to recycling. And great examples and what we compost a lot of are food service items. They just get too gunked up with food sticking to them or the greasy pizza boxes or what have you. It's not that there's no technology in the world that exists that can be recycled, that can recycle these, but it's not mainstream. Most recycling facilities will not accept these things. And think of all the wasted material going to the landfill. All of that desirable food gunk stuck to the paper plate that is going to a landfill when it could be composted and being used to improve the quality of our soils, to enrich our soils that so desperately need it, not only for agriculture to grow crops, but this compost can be used in remediation projects and construction projects. Soil that has compost amended can do a great job like retaining water, preventing runoff, preventing erosion. It's so important, and it's just, the biological circular pathway for these materials. Um, and, it helps to just kind of reduce the reliance on petroleum-based materials. And really, I mean, these certification programs are a great driver for just innovation of more biodegradable materials. We really need to move towards greener chemistries to ensure not just that we have compost, but that we're innovating with material biodegradability. We want these materials to last only as long as we need to use them for their use phase, but we don't want them to last forever. That's why we have the microplastics problem that we have, this micro size, materials out there in the environment lasting way too long. So really these programs are a great incentive to innovate and just important in general for advancing the future of greener chemistries for the health of both people and the planet.
Great. Thank you so much, Maya. This really helped. Lots of questions out there in the industry right now. So hoping this can help just, ease some minds and just get a little bit more education behind compostables and kind of what we do in our lab at Normec OWS.
All right. Well, thank you so much, Ashley, for taking the time to have this conversation with me. I appreciate it.
Thank you.